All right, hello. I'm Ted Bergin. I'm going to talk to you about the Origin Space Telescope and the formation of habitable planetary systems and all the amazing things we can do with this state-of-the-art telescope. And this is on behalf of the Origin Space Telescope Science Definition team. So first I want to motivate a little bit with this really cool figure. This is showing you the human body, right, and the percentage of elements that are contained in it. And of course we're mostly water. And by mass, we're mostly oxygen. And so if you really want to understand the origin of life, you need to follow the water. And that's a crucial thing, and that's something that the Origin Space Telescope is designed to do, is how can we trace the water from the beginning, when it first forms, when it's being supplied into a habitable world, and actually detect it in a habitable planet itself. So we want to ask the questions, where are these elements, and how can we watch solar systems form? And an amazing question to think about and try to answer is how we are alone, and we'll be able to do that. So an interesting question you want to think about is why would you want to go to the wavelengths that are capable of the Origin Space Telescope? So we're going to be probing from about 5 microns all the way out to 600 microns. And if you want to trace water, water is what we call light hydride. So it has a very large rotation constant, and it emits mostly small rotation constants, and emits mostly in the far infrared. So what you see here is this is a plot of the atmospheric transmission, where unity is meaning we're getting through the atmosphere, and then you go to longer and longer wavelengths here, or shorter and shorter wavelengths, you're getting significant absorption of water from the atmosphere, and you have to go to space to really detect water, and particularly its isotopal logs. What I'm showing up above in green there is a spectrum of light hydrides that are emitting just from a cold gas that could be representative of a protoplanetary disk or a core of gas before a star is born, and many of these lines here are actually water vapor. So the Origin Space Telescope will be able to probe from, again, 5 to about 600 microns. And the amazing thing is that we're going to have about a 4 order of magnitude gain in sensitivity compared to what we had previously in the far infrared from Herschel. And that opens up vast amounts of discovery space. In addition, we will be able to perform better than JWST MIRI, which will then open up our ability to search for inhabited planets. So the different instruments exist on this telescope, and we will have spectral resolutions all the way from resolving powers of 10 all the way up to maybe 10 to the 7th. So really get to sub-kilometer second resolution in some instances. So let's follow the water. This is a gorgeous image of our wonderful planet. And of course we have a water-covered world, but if you actually look at the amount of water that the planet has, it's actually a kind of a tiny amount. We're only 0.05% water by mass. And that's actually kind of interesting, right? If you think about it, it means we don't need that much for us to be here. So, okay, if the process is inefficient, we're still here. The question is, how inefficient is the process? And are there going to be some worlds that have more and some worlds that have less? And can we actually follow that? So we'll be able to trace water from the interstellar medium all the way into the protoplanetary disk, following planet formation and into exoplanets. And the first thing I want to talk about is the beginning stage in the interstellar medium. So this is a really amazing rendering of the Taurus molecular cloud. It's the closest star-forming region. I've never seen it like this. This looks awesome. This is from the Herschel Space Observatory, and all these red areas here and these white knots are actually stars that are being born. And with Herschel, we were able to detect water vapor from one of these dense knots that actually is before the star is born. So this little spectra, these blips here, are water vapor telling us it's present, and this star is actually, or this core is actually collapsing on its way to forming a star, and that water vapor spectrum is one of the ways that we know that is happening. So the next stage is following water into protoplanetary disks. So one of the things you want to think about is if you want to trace chemicals, you want to know how much of the chemicals are there. And so you actually have to determine chemical abundances. So that's a little tricky because hydrogen doesn't emit for most of the mass of typical systems. So this is a beautiful image of the HL-TAL disk from ALMA, which I'm sure many of you have seen. And what we want to do is we want to observe this in as many lines as water vapor as we can access, but also determine the abundance of water as a function of evolutionary state or as a function of distance. So one way to access H2 is actually to use its deuterium substituted H2, which is HD. This has an abundance of about 10 to the minus 5 below that of H2, but it actually is emissive, and it's about 1 million times more emissive than H2 is at the typical 20K in a public planetary disk. And so we can use the HG to actually measure how many Jupiter masses exist in a disk. And we can then determine chemical abundance as a function of evolutionary state. And with OST, we will have the sensitivity to survey hundreds of systems across spectral type and ages and really trace both total content and the evolution of the total gas content with time. And HD was first detected with the Herschel Space Telescope in 2013. Now this is the same view of that HL-TAL disk, but this time shown edge on in a different projection. And one of the things that you notice in the disk are these dark lanes. And there's theories out there about how planets first begin. And one idea is that when you get beyond what's called the water ice line, which is an evaporation front, so the water is ice at one point, and then it gets above 200K and the ice evaporates. And if you're at the stage where water is ice, it's thought that the ice-coated grains are more favorable to grow to larger sizes, and that's why we have Jupiters that form at larger distances and terrestrial planets a little bit closer in. So what we can do is look at these systems and actually try to determine where is that ice line, and what time, and how does that evolve. And how are we going to do that? Well, the neat thing is the Origin Space Telescope, with this tremendous spectral grasp, has the ability to detect nearly the entire rotational spectrum of water. Now, the James Webb Space Telescope is going to be able to observe lots of water vapor transitions, and it's going to be really amazing in filling in part of this picture. But the transitions that are accessible to James Webb all have upper state energies greater than about 1,000 K. So you're going to be emitting from very warm gas that's very close to the star. It's an important region. That's the region where terrestrial planets are being born. But if you want to have the complete picture, we have to go beyond the water snow line, because that's where we think the Earth got its own water. The Earth, we believe, formed dry, and its water was provided from ices that came from beyond this water ice line. And with OST, we'll be able to access not only the warm transitions, but also many, many transitions all the way down to the ground state, tracing 10K or 20K gas. And we'll be able to survey hundreds of systems all the way out to the distance of 500 parsecs and get true statistics on what water is doing during planet formation. So, Planetary Systems. So this is a beautiful movie of the Rosetta view of the comet, which I thought would just look great on this, and it does. And one of the things we can ask is not only, how does water get on other planets, but also ask about our own origins, which we kind of think is important too. And the way we do that is to use the deuterium fingerprint. The Earth has an excess of deuterium in its water. So this is a plot of deuterium to hydrogen in water in various bodies, for the most part, at least the ones that are up here. And the normal deuterium is in HD, so HD over H2 is a ratio of about 10 to the minus 5, but the chemistry in cold regions leads to an excess of deuterium. And so all solar system water has an excess of deuterium, which tells you something actually that water formed at temperatures below 30K. But then what we can use is we look at the D/H ratio of all these various bodies. So we have meteorites and the Earth here. They actually look about the same, and so that's suggestive that maybe meteorites or asteroids are where Earth's water came from. And here are measurements of many cometary systems, both from the Kuiper Belt and the Oort cloud. And so this is 67P from the Rosetta mission. Now, what you want to do is you want to ask, well, where is the Earth's signature? Well, right now, only one thing matches that. That's meteorites and asteroids. But, in comets, we only have tens of systems. And there's hints of diversity in that population. And so we actually don't really know And so with OST, we'll be able to survey hundreds of comets and determine their D-to-H ratio and actually work out the origin of our own water. We can also, with a very nice imager and our fantastic spectrographs, look at planets as they're being born in so-called debris disk systems. The Earth itself formed or finished its formation about 30 million years, and the gas was long gone, and rocks started banging into each other, and that leads to an excess of small dust. And so this is an AMA image of what's called a debris disk. So these are secondary, so there's the star. These are grains or big things banging into each other, making small grains that you see in this disk around the star. And the OST has the sensitivity to detect hundreds of these. And in fact, the OST will be able to observe actually Kuiper Belt objects which have their main emissions within our bandpass and survey hundreds of Kuiper Belt objects within our own solar system and determine their composition as best as we can do as well. So that gives us the trail. We're there, right? We have some idea about how we got our water and how other solar systems are getting their water. What about planets that actually have water? And with the OST and our unparalleled sensitivity, and we have access to unique features in the mid-infrared that we can point at and do transit spectroscopy of M dwarfs and determine whether planets around them, which we'll know in advance that they're rocky, whether they have features such as methane or ozone, carbon dioxide, water. So if you want to think about this, there'll be two so-called biomarkers that are in the system. That's methane and ozone. Ozone comes from O2. And with OST, we'll be able to survey tens of systems and actually determine whether we are alone in the universe. So I think if we want to look forward, this particular observatory offers, really tremendous opportunities for advancing our knowledge and understanding about why we're here. It's a very broad astrophysics mission, and I would like you to please take a look at it. The information can be found on the web under Origin Space Telescope. Thank you very much.